As our last example of calculating surface area, let's find the surface area of a sphere of radius a. Of course, we have an idea of what the answer should be. If you remember your surface area formulas, the surface area of a sphere is 4 pi times the radius squared. So we're expecting to get an answer of 4 pi a squared when we get done. Now, of course, since we're parameterizing a sphere, we want to use spherical coordinates. So let's adapt those. General spherical coordinates are given by this. X is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. So we'll take that, substitute it into the equation for the sphere. Now, hopefully you remember that in spherical coordinates, x squared plus y squared plus z squared is the same as rho squared, so we don't have to do all that trigonometry. And then rho squared equals a squared means that rho is equal to a. We're assuming here that a is a positive number. We then take that rho equals a and substitute back over here. That gives us x equals a sine phi cosine theta. Y is a sine phi sine theta. And z is equal to a cosine phi. So writing that in phi form, we have that our parameters are phi and theta, and our parameterization will be a sine phi cosine theta, a sine phi sine theta, and a cosine phi. Now remember, in the sphere, we need to go all the way from the North Pole to the South Pole. So that means that phi is going to go from 0 to pi. And I want to go all the way around the z-axis. So theta is going to go from 0 to 2 pi. So step 1 is to find the parameterization. That's our parameterization. Next, let's see if we can calculate the surface area element, ds. So I'll leave my parameterization down there. Let's find ds. Since my parameters are phi and theta, the formula for ds is d phi crossed with d phi d theta. d phi d theta. Let's calculate those two derivatives. The derivative of the parameterization with respect to phi is going to be a cosine phi cosine theta, comma, a cosine phi sine theta, comma, negative a sine phi. That's the derivative with respect to phi. And the derivative of phi with respect to theta is going to be negative a sine phi sine theta, a sine phi cosine theta, and 0. Now that we've taken those derivatives, I don't need my parameterization anymore. And I think I can remember that phi is going from 0 to pi and theta is going from 0 to 2 pi. So I'll erase all of this. Now I need to cross these two vectors, but I can save myself some work by factoring common factors out of each vector first. So first of all, let me notice that the derivative of the parameterization with respect to phi, I can factor an a out. That saves a little bit, not a lot. But in d phi d theta, I can factor out an entire a sine phi. And what's left inside is just a negative sine theta, positive cosine theta, and 0. And now let's take the cross product of these vectors. Now remember, when you cross the scalar multiples of two vectors, you need to multiply the scalar multiples and then cross the vectors. So d phi crossed with d phi d theta is going to be a squared sine phi times the vector you get when you cross these two vectors. Instead of using the ijk, let me just take the cross product and write the answer in vector form. In the I component, I have 0 minus a negative sine phi cosine theta, so that's positive sine phi cosine theta. In the middle, I have negative j, so that'll be the opposite of 0 plus sine phi sine theta. So that's a negative sine phi sine theta. And in the third component, I knock out this, and I take this determinant. So that's cosine phi cosine squared theta minus a negative, so plus cosine phi sine squared theta. Since sine squared plus cosine squared is 1, that just gives me a cosine phi in the middle. Now let's check that sign in the middle. It's feeling a little off to me. And indeed it is. This should be a plus right there. Sorry about that. I had 4 minuses instead of 3. I should have 4 minuses rather than 3. So when I take the magnitude of d phi dt crossed with d phi d theta, that'll be the absolute value of a squared sine phi times the magnitude of this vector. Now remember, phi is running from 0 to pi, and if phi is between 0 and pi, sine of phi is positive, and a squared, of course, is positive, so I can actually drop the absolute values. So I have a sine phi times the square root of the sum of the squares of those 3 terms. So that's sine squared phi cosine squared theta plus sine squared phi sine squared theta cosine plus cosine squared theta. Now here's the crazy thing. We've seen this happen before, but look. Looking just at the first 2 terms, I can factor out a sine squared phi, and that gives me cosine squared theta plus sine squared theta. So these first 2 terms combine to just give me sine squared phi. But then sine squared phi plus cosine squared phi is equal to 1. So I end up with a sine phi times the square root of 1, which is a sine phi. So coming way up here, ds is the magnitude of this cross product, d phi d theta. That's going to be a sine phi d phi d theta. Now this is a place where if you're going to be doing integrals over spheres a lot, you probably just want to memorize this as a special formula for the surface area element of a sphere of radius a. In fact, integrating over spheres is something that you do a lot in physics, so you'll probably find this formula in your table of formulas in a physics book. But remember, in physics, they often swap the phis and the thetas, so if you look up this corresponding formula in the physics book, it'll say a sine theta d theta d phi instead. So that's the end of step 2. A lot of work, but if you're integrating over spheres a lot, you just want to memorize this answer so that you don't have to go through that step 2 over and over. The last step is actually pretty quick. The last step is just to plug into the integral formula, which says that the surface area is the integral over r of ds. And in this case, ds is a sine phi d phi d theta. And the region r in the theta phi plane was theta went from 0 to 2 pi, and phi went from 0 to pi. Again, there are no thetas involved, so I can factor this out as the integral from 0 to 2 pi of 1 d theta. That is the integral from 0 to pi of a sine phi d phi. Here, since a is a constant, drat, what just happened? Somewhere steps ago, I should have had an a squared, and I did. So I apologize, I'm not going to remake the video, but I will remind you that I had d phi equals a times a certain vector. d phi d theta was a sine phi times a certain vector. And when I took the cross product, I had an a squared sine phi. And somehow I ended up not recopying that a squared. So this should be an a squared right here. I lost it a couple steps ago. Sorry about that. I'm going to pop that a squared right here, and I'm going to factor out that a squared here. Continuing to integrate, I get a squared times theta, where theta goes from 0 to 2 pi, times negative cosine phi, where phi goes from 0 to pi. So that's a squared times 2 pi, times cosine of pi is negative 1, so the opposite of that is positive 1, minus a negative cosine of 0, which is 1. So this is a squared times 2 pi times 2, which is 4 pi a squared, which is exactly the answer we were predicting.